All right. So those are the four things we will talk about. Regression is very much like your geometry class in which you found the slope between, slope of a line on a graph. And when I was a kid, it was y equals mx plus b. Is that what they still teach in? Oh, right.
It's not in the book that way, but yes, every teacher.
This is the same thing. We're taking points, we're making a line out of it, the line that best fits the graph. And remember when we were doing all those guesses, right? I could draw the regression line through it. That regression line is defined by the line that basically minimizes the distances between all the different points. It tries to get as close as it can to all the data points without curving at all. And we'll talk about that in a moment. The general format that we're going to use is y equals b sub 0 plus b sub 1x. Okay? And we could add to this b sub 2x2, b sub 3x3, and so on until we retire of it. But the b sub o is the y-intercept, and that is the value of y when x is 0. That is all it is. Okay, so when I'm looking at my little graph and I look at when x is 0, what is my value of y when I plot it on my graph? B1 is the slope, and it represents the amount of change in y that I see for every 1 unit change in x. So when x increases by 1, how much does y change? So, looking at this equation here, y equals negative 4 plus 2x. What is the slope of this line? Is it negative 4 or 2? Well, substituting in, the thing next to the x is always going to be my slope. Okay, so my slope is always going to be right next to my x. And if you think about it, it has to be, because when I change x by 1, that means I'm going to multiply that 1 point unit by 2. If my slope was 3 and x changed 1 unit, I would multiply that 1 unit change in x by 3. And what it says in this case is that every time x changes by 1, y is going to change by 2. The y-intercept here is negative 4, and that just tells me what my starting point is. When I don't have any value for x, what is y? When x is 0, is y also 0? In this case, it says, well, y is actually negative 4. So when you don't have any x, y is negative 4. And then as x goes up 1 point, my y increases by 2 points. So when x is 1, y is negative 2. When x is 3, or I should say when x is 2, y is 0. When x is 3, y is positive 2, and so on. And I can make a graph and graph out this relationship and see what it looks like. And if I pick a few numbers out of the air, this is what I would get. And as you can see, it's a positive relationship between these two things, right? How would I tell, actually, just by looking at this equation, whether or not it's positive or negative? What number tells me?
2.
Right. If my slope is positive, it means I have a positive relationship. If my slope is negative, I have a negative relationship. What if my y-intercept is negative? Does that mean anything in regards to whether I have a positive or negative correlation? Because here I have a negative y-intercept, but I have a positive correlation. Could I have a positive y-intercept and a positive correlation?
Isn't the negative 4 just the starting point of the
Right. So does that have anything to do with the slope, really? So that can be positive, negative, it doesn't matter in regard to the slope. Or the nature of the relationship, I should say. But the slope itself tells you exactly whether or not you have a positive relationship or a negative relationship. Now, I said this a second or two ago. but the way that you define what your regression line is and what the slope is depends on how it fits with all the other data points that surround it. And if you think about the mean is also the estimate that minimizes your squared errors. It's the midpoint, right? And any other point that I pick, say I have numbers that range 1 through 10, right? I can, and say that I have just 1, 2, 3, 4, 5, 6, 7, 8, 9, okay? I have those numbers. The middle of that's 5. And if I measured the distance to all the other numbers and squared them and added them up, that's the smallest number I can get. If I chose 6 as my midpoint, well, then I would have a greater distance square difference from here to 1 than I would if I picked 5. And well, it's not sounding very clear. I don't think anyway. But well, I should ask. Do you understand what I'm saying, or should I describe it in a different way? I usually have a whiteboard to draw on, and I don't in here. All right, well, I'll explain it in a different way. So, if we go into Excel, say, and say I have the numbers 1, 2, 3, 4, 5, 6, 7, 8, and 9, okay? Well, if I calculate the average, I get 5, right? That's the average. And the 5 is the point or the number that minimizes the square distance between my midpoint or my 5 and all the other points. Now, if I squared these things, if I looked at the difference between each one and squared it, I'm going to put 5 here. We'll try 6. We'll try 4. We'll try 3. We'll try 7. But you'll get the idea just from a couple. So this is going to equal this minus this only. Hold on.
You don't want the dollar in front.
In this case, oh, you're right, I don't. Never mind. Thank you, Shane. And then I'll. What's that?
It would work. But you don't want it.
Yeah, it won't work for the long term. So these are my squared values, right? Okay. 1 minus 5 squared is negative 4. I square that. 1 minus 5 is negative 4. I square that, I get 16. 2 minus 5 is 3. I square that, I get 9, right? And so basically I'm getting my sum of squares. And what the mean does, it minimizes my sum of squares. Any other value that I pick is going to make my sum of squares larger. And if I look at 6 or 4 or 3 or 7, it just gets way bigger. Oh, that's not right. 6 isn't right. Hold on. What did I have wrong here? Oh, I know why. Hold on. I need the A highlighted. There we go. That looks much better. So even if I move to 6, right, my square differences get bigger. They get bigger by 9. Same thing for 4. I'm moving 1 down instead of 1 up. If I move 2 down or 2 up, I go up to 96. So basically, I'm making the mistakes I might make a little bit bigger if I use 6 or 4 as my best guess rather than 5. And it's this idea of I'm trying to estimate or summarize a whole bunch of things or a whole bunch of people with one number. And I want to minimize the mistakes I make. I want to minimize my errors. And so 5, because it's right in the middle of everything, it's my best guess. I'm going to minimize the magnitude of my mistakes if I shoot right for the middle of the pack. Now regression is exactly the same. Only now, I'm in 2 dimensions rather than 1. So if I flattened all these people out and just looked at their x value, right, I would choose the mean of x as my best guess. But that doesn't take into account where they are on the y. So I could look at just their y values, and I could take the mean of y. But then, when I'm looking at how they rate on x and y, I have these 2 things to consider, and just taking the mean of x and the mean of y isn't really my best option always. So what I do is I mathematically determine what regression line, what linear equation is going to minimize the distances, or the square distances really, between each particular point and the line itself. The line represents my predicted values. In other words, because I have this line, if I know your score on an x, I can guess what your score on y is going to be. However, there's going to be a difference. Not here. This y is right on the predicted line. But if we look at all the other ones, there's a difference between the predicted value, which is the line, and the actual value, which is the dot. And I want to minimize the magnitude of those values. Those squared values, I should say. And when I represent my errors, my sum of squares of errors, I'm basically just looking at what is the difference between my y's and my predicted y's. The y hat is going to be my predicted y. Y is my actual y value. And my total sum of squares of error is going to be basically the sum of all those squared errors. Y minus predicted y squared added up for every single person. And my goal is to make that value the smallest, just like the goal of the mean itself, when I'm just dealing with one variable, is to make my sum of squares for that variable the smallest. So it does the same thing, only in 2 dimensions rather than 1. Now the last thing I want to talk about is the standard error of the estimate. And you can think of standard error of the estimate much like standard error itself. But the easiest way to conceptualize it, really, is the typical distance I will be away from somebody's predicted, or from somebody's actual score when I predict their score using my regression line. So it's basically, when you think of standard error, it's a typical mistake I make. So if I use my regression equation to predict what your college GPA will be based on your ACT scores, the standard error represents how many grade points I'm going to be off on the average. Sometimes I'll underestimate it, sometimes I'll overestimate it, sometimes I'll hit it dead on. But on the average, the standard error of the estimate represents how far away I'm going to be on the average. And we're not going to worry about doing this stuff. If you want to look in the notes, little values are filled in the comments. But we're not going to take our time with that today. I do want to talk about SPSS output. When we look at SPS output and we look at the correlation between any 2 variables, this is what we get. We get a model summary and a ANOVA table, because regression and ANOVA are actually the same thing. The math all works out to be very well the same, which is why you get an ANOVA table. Is interpreted pretty much the same way, only now instead of having sum of squares between and within, we have regression and residual. Conceptually, regression is still the stuff that I am accounting for, and residual is the stuff I'm not accounting for. So it's still, the F ratio is still a variance of things I can explain over the variance of things that I can't explain. I also get my coefficients, and we'll spend some time talking about these, especially when we talk about multiple regression. Sure, I got enough time here. First thing, model summary, we have a capital R. Now, a capital R is the multiple correlation. It is always expressed positively. So even if I have a negative relationship between 2 variables, this first R will be positive. The second one is my R squared, which just squares my R. very simple. And is my variance explained, or my percentage of variance that's explained. And then I have my adjusted R squared. R squared itself is too big. It always overestimates what the actual R squared in the population is when I use a sample to calculate. So what the adjusted R squared does is it compensates. In regression, it compensates for the sample size that I have and also the number of independent variables I have, because we're going to, as we go to multiple regression, we're going to have more than one independent variable. And so
we should always look at adjusted.
always look at adjusted. Yeah. R squared, people always report R squared, and people continue to do it. And if you have a big sample size, it doesn't really matter. But if you have a small sample size, the difference between these two can become quite large. And adjusted R squared can actually become negative in some cases, which is technically impossible, but it does. And then I have my standard error of the estimate. And this is saying, again, this 0.44 or 0.45 if we round up. It's saying that I will typically miss somebody's true score by about a half point.
That's an error of R? Or that's an error of the score?
That's an error of my predicted score. So if
Of Y.
Yeah.
Can you repeat what you said about standard error?
This is the typical amount that I will be off of your true score when I use my linear regression equation to predict what you're going to get. That's not what I said the first time. It's the same. Never.
You would call that vertical distance error.
Yes.
Do you ever call that residual? Or residual just to
Yep.
But that's reserved for what you can't explain.
Yeah.
I see what you're saying.
My
Okay.
model's saying you're going to be here, but I'm wrong by this much, and so that's my,
Yeah, that's, I get it.
So then the ANOVA table. My degrees of freedom for regression is just the number of dependent variables I have. And that's all it is. Residual, much like in our within subject sum of squares in ANOVA, it's just my total n minus the number of predictors minus 1. And in this case, my total is just n minus 1. But don't worry too much about it. Then I have my coefficients at the bottom. And these are the most important things that I care about. Now, I have first my B's, my standard errors, my betas, and then a t-test. Okay? My B's are my slopes and my intercept. My constant B is my y-intercept. So if you want to circle this and draw an arrow, this is my y-intercept. So if I asked you in this situation, what is the value of y when x equals 0, your answer would be 5.8. The next b down is the slope of this variable. And what this says is that when x changes by 1 point, y is going to decrease by 1.4 points.
It decreases.
Because it's negative. Now jumping over to the standardized coefficients, the beta. This negative 0.99 is just turning all my x's and y's into z-scores. And this is given in terms of standard deviations. So what this beta says, and it doesn't give the y-intercept because it's always what this beta says is that if I have a one standard deviation increase in x, I'm going to have a 0.99 standard deviation decrease in y. So with the betas, or with the b's I should say, I have unit increases, whether it's feet, miles, dollars, whatever. And in my standardized coefficients, my betas, I'm talking in terms of standard deviations. I also have a standard error because around these things. Because again, these are based on my sample data. I am estimating what these things are. I don't know what they really are. And so I always have an error associated with that. Now, this t-test over here, and this is what makes an individual predictor statistically significant or not, is testing whether or not it's a one sample t-test that tests whether each of these are different from 0. And what this t-value is this value divided by this value gives you your t. Again, this is like my mean difference, or my difference from 0, divided by my standard error, gives me my t-value, and then I have the p-value associated with that. So if the null is true, and the null in this case says that if the y-intercept is actually 0, I will get a t-value of this larger 4%, or 0.4% of the time. If I'm looking at the slope, and I usually don't care about this t-test. The only thing I care about in this first row usually is this value right here itself. I'm usually not interested in whether or not it's different from 0. Sometimes I am, but usually am. And then when I'm looking at my slope right here, this negative 1.4, right? This is saying that if indeed the slope of my x variable is 0, I will get a t-value of this magnitude or larger 1% of the time. Because it's less than 0.05, I reject the null, and I say that my slope is different from 0. Yeah. Woo-hoo. Questions on these things? All right then. Let us go back to our SPSS.
What software did you use prior to Whitewater? SPSS?
Yeah, I've been using it since grad school. I used Systat for a while.
They give us Minitab.
Yeah, you told me
A
that.
lot for the AP exam, and the only reason I think I can tell is that some of the older people that have their fingers into the exam are from Penn State.
Ah, there you go. Well, it takes on a whole new meaning.
I don't know if East Coast means Minitab or...
I don't know. Minitab seems to be falling more and more out of favor. I hear of it less and less. Usually, you can look at how statistics textbooks, what they put sample output from in, and I don't see Minitab anymore.
What sort of textbook do you use? Who are your authors that you use?
Gravater and Wallow. Those are the ones that I like.
Yeah.
I like their textbook a lot. It's very clear. I forgot who the other guy. I tried another guy once, but I don't like him. What's that?
What was the last name you said?
Wallow or Walno? I forget. Wallow. Anyway, go to the HSB data, and let's, instead of doing a correlation, let's go to Analyze Regression. And it's automatic linear modeling. I haven't even tried yet, so we're just going to go back to linear. I'll have to see what the automatic linear modeling, that's new for this version. Wow. Wonder what it does. Click OK, or just click on it, and let's predict word problem solving scores. So that's going to be my dependent variable based on reading scores. Now, if you click on statistics, we have a lot of options that we really don't care about now, but when we do multiple regression, we will. Most importantly, the part and partial correlations, and I want you to click that now, just so we have something to compare it to when we go on. We're not going to worry about collinearity or R-squared change. But we can throw in descriptives as well. What the heck? That's all we'll worry about today. and then click OK. There we go. All right. Now the first thing I get are my descriptive statistics. I can see what my means and standard deviations are. Whenever anybody does a study, you always report the means and standard deviations. It's just kind of a given. I will also get a correlation, and this is where I look to see whether it's positive or negative, because when I look down here, I might get misled by my multiple R or my capital R there. So I see that I have this really strong relationship between reading and my word problem solving scores, right? If I want to look at my model summary, if I asked you what percentage of variation in word problem solving can I explain by somebody's reading scores, what would your answer be? Would you go with the 0.956, the 0.914 here, or the 0.914 there, or the 0.826? And again, I'm asking what percentage of the variance in reading scores, or word problem solving scores, can be explained by reading scores? How many people like the 0.956? How many people like the first 0.915? How many people like the second 0.915? Hey, great, fantastic, excellent job. If I said how far away from somebody's word problem solving score am I likely to be? 0.826, right. Not even a point away, isn't that nice? If I look at my ANOVA table, how many people do I have here? Yes. Why would you get 600?
Degrees of freedom.
All right. Yes. Degrees of freedom total plus 1. The F again and the p-value. What this F is saying is, does my predictor significantly predict the dependent variable? That's the general question. And when we look at multiple regression in a little bit, it becomes more important to look at this because this is my model test to see if all my predictors together are predictive, and then this down here will be my individual predictor test to look at individual predictors and the contributions that they give. This p-value is, of course, saying that if the null is true and these two variables are not related, the probability of me getting an F of this large or larger is approximately nothing. Looking down below, for every time my reading score goes up 1 point, how will my word problem solving score change? Will it go up or down? How many people say it'll go up? You are correct. How much will it go up? Shane?
0.266.
0.266, right? This is my slope. And forever, what this means is that when my reading score changes by 1 point or increases by 1 point, I have a corresponding 0.266 change, a point change in my word problem solving score. How many standard deviations is that change? When I have that 0.266, how many standard deviations do I expect to change? Right, about 1, 0.956. Are these things different from 0? Actually, I don't worry about that. Is the slope different from 0? Is it a significant value? The answer is yes. This is the p-value I'm looking at. This, again, is testing whether or not this is different from 0. It is, and if actually in this case I square this, I get my F value. because f is just t squared when I have two variables.
Can I ask a question? I have to have kids do residual plots. How do I do that? I try tinkering with the theory. Mine is usually independent versus residual.
Yeah, if you want to look at, and this is actually something that I was going to cut, but I'll throw it in here now because somebody asked. We'll go to regression linear, and under your plots, the one that I like the best is having the y-axis be the z residual, and the x being the z predicted.
I did that.
Okay, good.
And I can read it okay. I'm used to having independent versus
Oh,
because they have to check.
Well,
They have to check. My students have to check the residual plot to see if the linear model is appropriate.
right. And when you look at this, if it ever works, come on. I think the big computer. If you look at this is a residual plot.
now the residuals are on this side. Now residuals, and I'm using z-scores, meaning putting things in terms of standard deviations and stuff. So anything that is above 2 or 3 standard deviations is pretty far off. I missed the mark by a lot. Big time error there. But what I'm looking for here is these are my predicted scores if I would draw a line right at the 0. That's my regression line. And this is showing me where everyone falls relative to that regression line. Now in a perfect world, one of the assumptions is regression is that I have almost elasticity. Don't worry about the word. But it means that I have a uniform and normality of my residuals, meaning that I have basically a uniform cloud along the whole range of my predicted line. In this case, if you look at this, I have this kind of smiley face, which means that when I'm predicting people on the low end, I'm underestimating their ability. When I'm predicting people in the middle, I'm overestimating their ability. And when I'm predicting people on the top end, I'm underestimating their ability. Because if you look at this, right, in my regression line is right here. The vast majority of the people at the high and the low end are above that regression line. They should be equally distributed in both ends, but they're not. And so I'm underestimating them systematically. When I look in the middle, I have too many people actually focused below that regression line. And again, people should be on both sides. And if you would look at this, you would say that, well, it's not really linear. And if I wanted to, I could even put in a line. Well, I should not even bother. My computer's acting too slow. Too many clicks. I can put in a line if I want that represents the line of best fit, and I can make it curve if I wanted to, but I'm not even going to bother with that because it will take too long. Wow. How you take your computer's, jeez. There we go. Come on. But I need to talk about that, the coefficients. Where is it? Here it is. All right, one thing we still have to talk about are the other coefficients. We have a zero order, a partial, and a semi-partial. Correlation. Yes.
You mentioned that D is in units and beta is standard deviations.
Yes.
And I should know this by now. What is T then?
T is a ratio again of, this is my observed difference from 0. This is my expected difference from 0 based on my data and my data point here.
How come it's not expressed as like 0.7, or is it like, would you still,
It's a very, 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 very big ratio.
Yeah, because in this case, if I divide this by this, think of moving the decimal places over 3. It's like 266 divided by 3.
Okay, I thought it was a ratio, but then it was so big. And then you can have a negative ratio.
Yes.
Okay, that makes sense.
That just means, right, if this top number is negative, my t-score will be negative. And in the case of my slope, if I have a negative slope, it means I have a negative relationship. So when x increases, y decreases.
Thanks.
Sure. Now I will have here my zero order, my partial, and my part correlations. And I want to talk about these things before we get into multiple regression, just in the sense of what they represent. Now here they're all the same because I only have two variables. The zero order correlation is my basic correlation that I've been talking about the whole time. My partial and my part are going to be correlations that factor out different aspects of other variables I care about. And as we go forward, we're going to see that my partial and my part are usually smaller than my zero order correlation. Not always. And basically, I'm going to use the partial and the part to identify kind of unique characteristics about the variable that I'm looking at that moment. But we'll get there in a minute. So, if you want to open up the multiple regression notes, come on. I really don't feel like I'm asking my computer to do too much here. All right. Multiple regression is really when we have more than one independent variable that we're using to predict something. So I want to know what my risk for dying of heart disease is. I'm an American male, right? I'm concerned about these things. Number one killer, right? I want to know what my probability is. Well, there's a lot of reasons why people have heart failure. Some of it is their diet, some of it is their stress, some of it is genetics, all sorts of things. Each one of those things explains a little bit more of why somebody does or doesn't have a heart attack or have heart disease in general, or any bad thing happen. And so we can use multiple predictors, and we really want to use multiple predictors because if we just look at individual pairs of variables, we can kind of be led down the wrong path, because if we don't think critically about what the variables we're using, we tend to make mistakes, and I'll have a couple examples coming up. So we'll talk about reading the output and looking at the model and how it changes now that we have more than one predictor, and then looking at those individual predictor results. So more examples. We think about therapy effectiveness, whether it's psychological or speech therapy. Some of it has to do with the skills of the practitioner, whether or not they connect with the person, get them to work outside of class, convey the importance, all sorts of things. The type of therapy, the amount of practice that's going on, physical, local, technology limitations, all sorts of things, right? Same thing for pizza tastiness, right? Quality of the crust matters, quality of the sauce, the amount of cheese, the ratio of those things. You can have a pizza with too much cheese, believe it or not. I think I said this before. Have you ever eaten at Marty's Pizza? Conomowoc or somewhere, Delafield, something like that? A lot of cheese on that pizza, if you recall. I will never forget that, because when I was a younger person, I could eat, large, whatever, Pizza Hut. That's what I would eat for lunch. I would just eat a ton of food. And I remember I went there, and I had 2 pieces, and I was stuffed. And I couldn't believe it. And it was because I probably ate 5 pounds of cheese. It was just falling all over the place. So if you like cheese, it's a great pizza to get. And then you have leftovers. So that's great. But otherwise, there's all these factors that go into why something is the way it is. When we try to simplify things, we tend to run into problems. So I'm going to give you this graph right here. And we'll talk about firefighter funding. Very appropriate for the dry conditions we've been experiencing. And we look at this little graph here, and it's a government official comes in and says, well, look at this. I have this graph about the damage done to buildings and millions of dollars, and I have number of firefighters deployed to each of those blazes, right?